again, hello. Thanks for coming this week. Everyone was able to get on Ax and get the curve note and get the meeting notes up and start typing away. Make sure to add quick reports and things that you'd like to talk about on there again. Is there any sort of announcements before we start getting into some quick reports? Anybody? I don't really quite know of anything that we need to announce or I think next week we'll try to do an after meeting hacking thing. I'm trying to get back into doing it every other week. So it'll be next week. Next Wednesday will be after meeting coding.
Actual coding next time.
Yeah. Yeah. This past Friday, we talked about a little bit of a few little things, and helped each other where we did, and just kind of had a nice social hour. It was good. John, I see you've added some stuff in there. Would you like to go first, please, with your quick reports?
Yeah, sure. Yeah, I'm just wrapping up the MT right now, that simulation MT. There's just a couple tests, and it looks like it's got something to do with like the docs. Yeah, I might need a little bit of help. Just if someone, or there's a little help of what that's pointing me at with the error. I just can't really find out what it is exactly in the docs, but yeah, I'll touch base later. And then I'm just running some large scale DC tiled inversions. I had to wait till this morning to start it, but it's running, and yeah, I'll see what the timing is and how it works. And then I've also taken on getting the MVI examples and MVI tiled stuff going. I got dropped a huge airborne data set that needs to be done. And yeah, I'll work on that. That's about it.
Oh, glad to hear it.
John, DC tile, like did you have any problem with the memory, like or was that?
Well, we're writing it to disk right now, so it's a little slower than trying to store it all to RAM right now. Yeah, the computer that I got has only got 1 terabyte, and this one's probably going to be a little bit more. So I'm just writing it to disk right now, and it's doing its job. It hasn't finished yet, but yeah, it's doing its job.
Yeah, I would be curious, like how big is that kind of thing? Like you're like how big you're storing a big thing.
Yeah.
I'm also curious about the number. So if you can let us know the number, so like
Yeah.
kind of just a quick number about number of data and number of cell size and the matrix size, it would be kind of interesting to sort of know.
Yeah, for sure. I once I get some hard numbers here after this run, I'll let you know. Because yeah, I don't know how big this is. Like you can do like some kind of guesstimation, but it so far when I've run them, they've always come out bigger than what I expected. So we'll see.
Good. Well, okay, I'm glad to see it working at least for now. Hopefully, every new data set presents some of the challenges that we can hopefully use to make SimPEG better. Right? That'll be great. Dom, would you like to go? I see you on the next quick reports thing there. Don't mind.
Yeah, man. So this weekend I continue testing the tiling for the FEM. I posted the slides there that I'm just appending as I go. Basically did a 9x9 3 frequencies airborne style system over a block, and then compared the traditional way, the storing J, and then some like frequency tiling, and then the speed up is quite amazing. I don't know if you guys seen the numbers, but we went from like 86 minutes for 5 iterations down to 4.5 minutes, just storing the J. And then about like roughly another 25% decrease if we start tiling here. Obviously, tiling on a single machine is not, has its limitations because eventually Paradiso is fully booked. But yeah, basically a factor almost 15 year speed up. So it'll be really interesting. Now I'm trying on the natural source because it's exactly the same Dask implementation. I actually have nothing to do. It's using the same calls. So I'm just trying now on the natural source. That's it.
I mean, so yeah, it's good that we're able to get some of the MT stuff unified under that framework then, so we can take advantage of it.
That's right. Yeah, it's the exact same functions. I initially created a natural source Dask, but don't even need it. It's basically the base FEM that handles it all. So it's all good.
Cool.
Again, here, it might be actually worthwhile to count the number of solve. Because I kind of have the similar experience with the DC, because actually storing J was faster than not storing J, which is like somewhat surprising. So it might be actually interesting to, because like basically count, like if you do non-store J, then we got lots of CG and lots of like a solve of JBAC and JTVAC. So it might be worthwhile actually just like the count, how many, like for a single inversion, and let's say 5 iteration, basically counting how many solve we need to get to that solution. And actually that kind of give us, okay, why that's actually much faster, because otherwise it seems like somewhat unintuitive. Like in general, storing J is expensive and like actually requires more solve. But what we're getting is actually storing J is more efficient. So yeah, getting a number, it might be a good way to just check, okay, that makes sense.
So you want to have basically the crossover point, right? When how many CGs that eventually storing J gets more efficient. Yeah, I get it. Yeah. Because here I'm doing 20 CGs, right? So
yeah,
that's
exactly.
why the speed up is that way.
Yeah.
If we only do one CG, then probably the non-storing will be faster. I totally agree. Yeah.
Yeah, I'm not sure what is the default CG in UBC code, because I guess like it's not 20. I'm pretty sure it's 325 or something like that.
Yeah, 4 or 5, yeah, something like that. But you see, in order to be able to get that result that I'm getting right now, we're sort of getting, about the right depth for the block. The inversion is right. We need to bump our CGs. If we undersolve it, the result looks crazy. So it's important to solve it well, right? I'm just gonna finish saying that.
Anyway, yeah, I mean, like as long as we do a apple-to-apple comparison, I think it's fine. So.
Mhm. It might also be a little bit in there that we're able to take advantage of like the Paradiso parallelism a little bit more when forming J. Might also be, that might have something to do with it as well, even if there ends up being a few more solves.
Yeah, that's what I started to encounter with natural source, right? Because we need to cycle through the data on each receivers, and they have multiple ones. I think it's going to be more efficient. We start stacking them rather than calling Paradiso, looping through all the data basically. Because right now, natural source is still pretty freaking slow.
So are you telling me that the number of solves of CGs has to be like hard coded in there, or why not have it stop after reaching some kind of tolerance?
Yeah, tolerance is fine, but usually we never reach a tolerance. We quit before we reach it, right? Because it's too expensive.
Yeah, it's like to reach some of these like some of the common tolerances, it takes hundreds, sometimes, of iterations. Even if you have a good, like if you have like the default CG solver in like SciPy, like it can, like depending on the system, right? It's hundreds, thousands of iterations depending on the condition, things like that.
And that's an open question to the group too. Like, what is the right tolerance, right? It's kind of a magic number that we pull from thin air, but I don't know. I don't have that answer. I don't know if anyone knows here, but yeah. But Devon, yeah, it's the same as usual, right? It's either we cut it off after a certain point, or we have a magic number as a residual. Yeah.
Yeah, it's a question of like, are we going to make a very small incremental step or have a really good one step? I don't know. I think what Eldad actually said initially in his a lot of courses, we don't really need to solve that well. So like that was the kind of like idea of having a few solve because we're doing it multiple time. But in practice, I wasn't sure what's exactly the better way. I don't know.
Yeah, it's one of those, it's kind of like, okay, well, the gradient, and yeah, you get a little bit better convergence criteria or convergence in general if you do, an accurate solve, but the gradient's already a downhill direction anyway. You're just kind of moving it when you do CG a little bit. So
Someone can try it. Someone can test it. I think conceptually we want to do it well, right? Because otherwise we don't know what we're minimizing. We're already doing, Gauss-Newton steps, so we're kind of guessing that we're minimizing anything if we're not really doing the CGs well. But.
Yeah. Sean, would you mind going next? I see you added one at the top there.
So last week, I spent all my time to deal with the reviews comments for manuscript, and Dom is one of the review. And I also performed the field GZZ data inversions multiple times over the diagram areas. Maybe can I share my screen for a moment?
Go right ahead.
Okay. Share. Can you guys see my screen? Yeah, last week I implemented the field data inversion. Here is the data maps, and I just random sample different adjustable parameters and perform inversion and obtain the recovery density models with different characteristics. Some of them are really compact, and this one is a little bit smooth. And similar, this is way more smooth, and these models are really compact. I just performed these inversions a total of the 160 times, and then I, based on the borehole data, to decide which model are acceptable and which are rejected. Finally, I just calculated the standard deviation to analyze the uncertainty of these areas. This is what I did the last week. Yeah, that's all from me today.
That's cool, man.
So, can you explain? I'm sorry, I missed it. Can you explain what the suite of models were that you were looking at? What you were varying?
Oh, you mean this page?
Yeah.
So, oh, sorry, what's your question?
Well, I was just wondering what is being varied to get these different models?
Oh, for here, I randomly tuning the two adjustable parameter. One is RFS, the weight for the smallest terms, and another is the norm values on the smallest terms. I just random sample these two parameters from a uniform distribution and implement the invariance.
And then the range of sort of like an order or 2 orders of magnitude for the alpha S?
Yes, the RFS.
Just trying to see. Yeah.
Just a random sample the RFS between the really small.
Okay. So, all right. So now you've got these models, and then you're just going. What are you going to do then?
And then I just so for here, this black dot is well locations, and we have the drill hole data and in these areas. So after perform the inversions, I obtained a large sequence of recovery models, and then I implement the drill hole data to help me make the decisions, say which model are acceptable or which are not, should be rejected, because these recovery model cannot satisfy the drill hole data. And then I calculate the standard deviation of all the accepted
So
model.
basically you calculate, you generate a whole bunch of models and you've got one calibration point and you look to see at that one calibration point, which of the models is like the closest to that, has done the best job at predicting that. And then you use that for the, as a basis for looking at the whole set. Is that correct?
Yes, that's correct.
Is that, are you like determining accept or not using that one point? Is that like you've got 100 or 150 sets. So if that match with the well, you accept. If that doesn't, you don't accept. Is that what you're doing?
Yes.
Ah, I see. And the slide 4 is basically like some sort of variance within your model.
Yes.
Okay.
Yeah, this part work is primarily to do with the DOM's comments, how to determine the optimal range of these alpha as values. We're lucky have a tree-hole data in these areas, and then we can decide which model are good or not.
Right. And then how many like you had to remove by that one point?
You mean the how many invariants I perform?
No, like how many points, like how many models that you had to remove? How many models weren't matching with the borehole?
I performed the invariant 160 times, and there are only 28 models are acceptable in this area.
I see. So you basically throw it away 140.
Yes,
Left
basically
with 24.
acceptance rate around 20%, I think.
Okay.
And what are you using as criteria, Shalom? Is it just the values of the model, or is it like where contacts are? Like what's the acceptable or not when you compare your model to your borehole?
So for this well locations, we have the report, and we know the lithology of this part is metal gabbro, and then we calculate the mean value of the metal gabbro from the recovery model, and then we comparing this mean value with the tree hole data. Mean value of the recovery model with the tree hole data. Yeah, that's all from.
Yeah.
Would you like when for the page 4, isn't it better to somehow transform your susceptibility into orthology and then getting a variance of orthology? Because I mean, as a geophysicist, I care about the variance in the magnetic susceptibility, but in general, like people don't really care about, okay, there's like variance in the susceptibility, but what people may care is in, okay, what is the variance in orthology? Like how much uncertainty that I have to determine this as a certain unit. I don't know. It's like just in general, like thinking about your clients or audience, maybe they may care about more about that, I guess.
Yes, I think so. Yeah, this is what you said is exact what I'm going to do next. I'm going to use some geology differentials to identify the different geology units. And in this case, we can identify the uncertainty or variance of the different lithology in this area.
And the other thing, like, expect if that's the uncertainty, I would expect much higher uncertainty at depth. But then that's not really captured in here. So I don't know, like if I'm a reviewer of your paper, that would be my first question. Okay, why I'm seeing very small uncertainty at depth? Because I know there's large uncertainty there. Anyway, just a few things.
Well, it is though, right? Because the top of the anomalies are much like the white band is much thinner on top of the anomaly than it is at the bottom of it. Right, you see the cross section in the middle there, like the white and red spot is like basically all of the bottom of the body, right? It's not on top. The top of the body is always fairly well constrained by the data.
Yeah, so that's somewhat confusing, right? Like, so you have a large standard deviation where you got high confidence, I guess, because you're pretty sure about that block is there. But what the standard deviation says, oh, it's pretty uncertain at that part. I know why that's happening, but like I said, it's somewhat like a misunderstanding. It's because like when I'm looking at the standard deviation map, what I'm looking for, like a red value, is highly uncertain area. But what you're showing is actually high confident area. So it's somewhat confusing. So I would like kind of either normalize and do something to show where are the uncertain part as red.
Okay.
And that's because the density values are changing so much, right? Maybe you need to, before you do your standard deviation, you need to normalize the values, as Sog said. Because in the middle of the body, you're pretty confident the body is there. You should have a very low standard deviation in the middle of it, right? Or the top.
Yeah, so use the mean Sierra Leone way. So use the mean of the model to normalize, and then you can show both.
Okay.
That's probably.
Yeah. Yes. Yeah, I think so. Yeah, it's a good idea.
Why the mean, Sog? Sorry, we're dragging here, but why the mean?
So like you got lots of models. You take the mean that has like somewhat representative what's happening in the model space, and then you got a variance. So if you divide that variance by mean, it gives you the relative like changes in your model. So that'll kind of show where the uncertain part more relevantly in this case.
Yeah. That's all from me today.
All right, thanks for sharing, Shalom.
So I just stop the share.
Lindsay, would you mind going next to see your next on the list here?
Sure, I'm more announcements on things. I copied in a message from Sarah Gare. She got in touch. She's helping organize a small EAGE workshop. And they're going to do a session on sort of open science, interactive initiatives for sort of education and science and geophysics. There's a link there, and she was wondering if one of us or multiple of us would be interested in giving a bit of an overview of SimPEG. I think it'll be pretty informal. I mean, we might have a couple of slides, or it might just be kind of ad hoc. So if there's folks, I mean, I'm happy to potentially be a part of that, but I'd be very happy to see other people sort of jump in if this is a community you'd be keen to connect with. And if you want to take a leadership role on that, that would be awesome. I'm happy to be support staff. So if somebody wants to take lead on that, yeah, I'd appreciate hearing your thoughts. And then the other one is that Sean Walker is giving the Subsurface Rendezvous talk this week on Friday. I think he's planning to use SimPEG a bit, and he's doing it's really going to be a discussion on noise estimates in inversion with DCIP. So I dropped the link there. I don't know yet if I'm going to be able to be there, but I would encourage folks to go and give us a bit of an update afterwards, because I think it'll be a really interesting discussion.
Do you know much about this forum or what's happening? I hadn't heard about it.
So what it is it's basically, okay, so for timing, it's on the, I think it's at, 10 a.m. Central. So it'll be a little early on the West Coast. But basically what it is it's kind of like an offshoot of the Transform conference idea, but this is a little more scoped, and there'll be sort of multiple of these, I think, throughout the year. So I think it's really meant to be like Sean is going to give a bit of a presentation. And then he posed a few questions that is really going to be sort of a discussion. Yeah, thanks, Tom. So there's a link that has a bit more of a description on that, but it should be sort of like a mix of presentation and discussion. So I think it should be a pretty good session.
Oh, okay.
I talked to Sean a little bit, and he has he's creating a directive basically to reweight the errors on the fly, right? So that'll be quite interesting to see.
Oh, cool.
Yeah, I think it's a neat strategy. I'm interested to see how his results.
Did somebody say you dropped a link?
In the
It's
chat,
in-
yeah,
It's in the notes and
Oh.
in the Zoom chat.
Okay, got it.
Yeah. Yeah, so I guess on the first point does anyone, I mean, I'll just put the question on the spot. Does anyone want to take lead on the EAGE workshop?
What is the timing on that, Lindsay?
It'd be April 27th.
I don't know about the lead, but I can probably help, yes.
Okay, cool.
Yeah, I can definitely help as well. I can possibly lead forward with it, but I need to double check my times and things and other commitments.
For sure. Okay, well, I'll leave that open. And if anyone, just follow up and feel free to ping on Slack and we can get back to Sarah in the next few days or next week.
Cool.
That's it.
Devin, I see it. See you up next in here, if you don't mind.
Yeah, I'm mostly chipping away at the same stuff that I have been working on for the past few weeks. So I'm not sure you saw, but I've merged the work that I did on EM1D into our base EM1D development branch. So the methods are the 1D stuff is kind of partitioned into frequency domain and time domain EM, and now we're sort of ready to plan on the next step. So seemed like a good idea to bring it in because the tests have been updated, the tutorials have been completed and added to the docs. So yeah, we can kind of come up with a global next step for that, and just waiting for review on the discretize tutorials. So I got some feedback from Doug and Lindsay a week or two ago. Made some improvements on how we do the tutorials, expanded them, and now I'm just looking for some feedback on that. So yeah, maybe I guess. Sorry.
Yeah, I remember I've looked through them since you've updated them again. I think it's definitely on the right track as far as the discretized information. A few things is that some of the pages definitely seem very repetitive as well, even though we've cut them down some.
Yeah.
At least to start to a few of them. I just had a thought on something else and it slipped my mind.
Yeah, and there's a couple of, I guess there's a little bit of functionality that I'm hoping discretize will have before I complete them. And one of them is just, I know it's basic and we don't really use it for EM, but the nodal inner product matrix. So I may even just do that for the tensor mesh, just so that I can put in complete sort of an inner product example and call that. But yeah, there's and I'm looking forward to when those the boundary conditions on differential operators is finished, but I know that's not trivial. So there is some stuff that I'd like to add to it once my wish list of discretized functionality is in place.
Good. It came back to me what I was going to say on the tutorials. What is everyone else's opinions as far as whether, like, if you're looking at tutorials, if it's more helpful to see, like, in documentation, if it's more helpful to see code like bit by bit or just big chunks of code and then comments and descriptions outside of them?
Bit by bit for me.
I agree.
Me too.
Okay. So then I would see if there's a way that we can break up the bits of code a little bit more that are in your tutorials.
Oh yeah, that would be pretty easy to do. I definitely want to make sure that there's a very strong heading that says, okay, we're going to do this separate thing now. guess
Yeah.
the thought process was to try to keep each example very separate. And as long as that's obvious, there's definitely a way to have, yeah, you know, the 2-3 lines of code and then a few words. So instead of, I guess basically what you're asking is, instead of having the kind of some information, instead of having it as comments, to take it out of the code block and then just have it as words. And then when we're actually running the lines of code, that's in sort of the code box, and that's easily changeable.
Sounds like a good idea. A good plan. I'll go through and provide a few more detailed point-by-point comments as well soon.
Yeah. Well, once I
I think that
amass
leaves,
all the comments on everything, then we
yeah,
can just do the next step.
I think that leads into what I was going to be talking about next.
Yeah.
So
Go.
one of the things in MT1D I've outlined, I put in a few like kind of action items that I'd like to see addressed before it gets all merged into master. There's a few things on there. When looking through the code myself, I think they're all things that can be done. So things like, okay, well, first of all, the simulation classes should be renamed to go along with the convention that we have within SimPEG already. So I mean, that's an easy change, easy fix. Looking at how the receivers and sources are structured, I think we can get away with just using the ones that are there without, I mean, maybe possibly adding a little bit more functionality to the classes that already exist. But I think it should be pretty easy to make use of the existing sources and receivers. At least for the frequency domain one, that'll be really easy. And the time domain will likely require a little bit more thought as far as unifying them. There's a few other items in there as well that I've kind of outlined. The other thing I wanted to bring up is that, so within the simulation, like the EM1D, there's a lot of, you can invert for things like the col parameters and a frequency domain, a frequency dependent connectivity, right? Like I see the option in there as far as the simulation. It seems to me like it would be better served as like a mapping. However, I'm not sure of the current place of like frequency dependent properties in SimPEG.
I agree. We don't have. I agree. In general, though I wasn't sure. Like, so the current implementation of col in that IP code, it's have a look. I have a look at the SIP example because it's more convoluted. So I wasn't sure. Like I can really break it apart as a mapping because I had a hard. Like in general, I thought I could do that, but when I was implementing, that wasn't that kind of distinct to be separated. So yeah, currently I have an internal function that kind of does it, kind of mapping like function. But yeah, I'm pretty sure we could do that, but I wasn't sure implementation wise. It's like it's very clear to kind of make that as a mapping.
Yeah, I think that the issue is like kind of what I've said. It's that we don't have a concise or a clear way of implementing those frequency dependent properties. Like how I'm not sure if there's a good way that we can take advantage of them within. I mean, they're certainly not supported in the current frequency domain codes, right? It's all the connectivities have to be, or soon to be, constant throughout every frequency that you give a simulation, right? So
yeah, I thought it's a little bit better, like kind of, if you, for instance, let's say if you're using col, having a separate property of eta tau c, because like for instance, like just thinking that as like a separate property, that's how it's implemented now. And I think it's a bit better than like generating a mapping. I don't know. Maybe I'm wrong, but anyway, that's how it's implemented so far.
Yeah. So that was just one of the things I was wanting to discuss here. Is kind of seeing a path forward, because the point is, like, if we have those frequency dependent properties and we get them working for other methods, like there's no reason that we can't use the same, cold models or whatever within a frequency domain EM system, like the frequency domain EM modeling. I wanted to be able to take advantage of that and be able to apply it to more things.
Isn't just a wire?
Yes. Yes.
So you would
But
have
I
like
think
you have
it's-
sigmas for a bunch of frequencies, and you just wire to the right simulations, right?
Right, but I think Joe is going one more level, like having a cold mapping, and then the wire is attached to that mapping, so you got multiple properties. So yeah, I think it would be ideal, Joe, but I wasn't just sure how to really do that now.
Kind of seems like one of those things where it's you want to add a detail and then it's ballooning into a more like global SimPEG type project, and I really want to avoid that.
Oh no, I understand. I thought it was worth having at least a conversation about frequency dependent properties here.
Yeah, I mean, I also thought that the Cole model in some ways is it seems like it's a very widely used model for the IP effect, but I don't think it's necessarily the only model that you could use to describe that effect that would explain the data over that range of frequencies.
Yeah, and like and then if you think about it like that, it kind of makes sense to be able to, okay, well, let's define a different mapping for frequency dependent connectivity and see how well that applies.
Yeah.
I think the first step, Joe, maybe just like expanding the current assumption about real conductivity to complex. That's probably a first step. Then if you want to parameterize, then we can have another mapping that could parameterize like, so now you need to connect the different frequencies. So it adds a little bit more complexity, but yeah.
And I guess, Sagi, with your research, I guess it's been a while, but you're kind of recovering an independent like frequent you're going to recover a complex conductivity for each frequency, and then in your regularization you have something that kind of tells you that the I guess the conductivity over each frequency has to have some kind of shape. It's constrained in some way, or did you do something completely different?
I think my PhD was like kind of like that. So you do a separate inversion, and then you do a post-processing to extract whatever call or whatever parameter in IP. So yeah, it's pretty clear, close to what you have said.
If I can make a comment here, that trajectory of excuse me, just working, getting into the complex domain for conductivity, and then having options for how we want to treat things, because there really are quite a few ways that people tend to think about how to parametrically represent that complex conductivity. And yeah, so co-parameters is one, but there's also a lot of others that take place. So having that flexibility would be good.
So it almost seems like we need a special property. Okay, we have these, like the way that we define the things right now, right? It's like, oh, this is a density model. This is a scalar. They're all scalar properties right now. So it's like we need an extension of that class to be able to have, oh, this is a complex property. This is a complex frequency dependent property. This is.
Yeah, we need a real and imaginary amplitude and phase into our model property.
There'd be a way to do it, right? You could always put in that that real conductivity as a property, and then yeah, either as your infinite or your DC conductivity, and then you could have a second parameter, which is basically the difference from that, basically the IP effect. So you could have a real conductivity, that's your standard. The other one you never have to use, so it's really easy if you're only dealing with real conductivity. And then you just have a perturbation from that as like the complex part, kind of like having a sigma and a delta sigma property. Does that make sense?
Yeah, and one thing that we should talk about too that I started doing and we haven't talked about is that right now only simulation has mapping, but in the case of tiling, the misfit should have a map as well, and it could have a data map and it could have a model map, right? So basically, after the simulation is done creating the fields or whatever doing its thing, the misfit knows how to transform this into something a little bit more higher level. And then that's something that we need to talk about at some point. Having mapping on other objects than simulation, basically.
Explain a little bit more why, like a misfit knows the simulation, which knows the mapping, and why do we need like a separate mapping for misfit function? Like it's sort of like propagated through the simulation, I guess.
Well, in the case of tiling, right, we're doing a projection from a local mesh to a global mesh. But the simulation cannot know about that projection, because otherwise when you're computing your sensitivities, you're basically computing sensitivities for the global mesh, right? Because it's doing inside the J call, it's doing the derivative of the mapping. So basically you would be projecting right away to the global mesh. We want the simulation to only know about the local mesh. So that means the projection needs to happen outside of the simulation. It needs to happen after, J vec has been computed. So then if the misfit has it, simulation does its thing, it's compute, it's A matrix on the local mesh. It's doing its paradiso on the local mesh. It spits out a small vector, and then the data misfit can grab it and project it to the global. There's no way around this, because mapping, if the projection is inside the mapping of the simulation, then everything is global mesh. I don't know if that makes any sense to people, but that's just how it works. Because A has the mapping in it, right? A of the simulation has its mapping. Yeah.
Right, but your model is defined on the global, I guess, right? So you always need a mapping anyway to generate the physical property in your local mesh where you solve your PDE, I guess.
Yeah, but if misfit has a mapping to do that reverse projection, when we call, when the global misfit is asking for a deep red, then you can just do the map and pass this model to the simulation. So basically the misfit is sending a small vector to the simulation. Simulation only ever see, its own local map, do the operation, and send back its local vector. And only the misfit knows about the projection from local to global. Does that make sense?
Conceptually not. I sort of understand why you're doing that, because conceptually, our local simulation needs to know the mapping that I can map global model to your local mesh. So as long as your local simulation knows that, there's no need to pass another mapping to a misfit function, because we're passing the simulation to the data misfit function. But I guess your problem in parallelization is more because it's kind of heavy. So I think it's more like a
no, it's not about being heavy. It's not about being heavy. It's is that if we want to store J, we want to store local J's. We don't want to store global J's, right?
Correct.
Yeah.
Right.
But there's nothing preventing us from putting maps on whatever we want. We don't have to be dogmatic about mapping is only on simulation. Anything could have a mapping, right?
Yeah. One other thing I'd like to talk about is put some notes on boundary condition stuff. I'm working on getting the averaging operators that we would need. So essentially everything has a corresponding boundary integral. So like normally when we're doing weak form, we're talking about volume integrals over the mesh, and things are defined at different locations. Well, now we also have to think about the boundary boundary integrals on those same kind of operations. And some of them are not as easily defined as the others, like as some of the boundary integrals. Like it's harder to find some of them with cron products, just because of the way that like structures, like if you think about edges, some of the edges are shared by multiple different types of boundary faces, and it's a little bit thoughtful sometimes. So I've gotten some of those implemented nicely. I have a few of the weak form boundary integrals defined for edge curls and face divergence right now. Those kind of boundary integrals. They should work on any of the structured meshes. Generally, how I have them set up, so I have them in terms of just kind of, face. I basically broken them down with the same similar types of operators that we have for the edge, like the inner product matrices that we see from the weak forms. It should be easy to extend it to the tree mesh as well. The other question I have is that, so when I'm coming up with some of these like default matrices that we could assume, so I'm trying to put in the tools for people to implement boundary conditions on their own as well. But I'd like to have a few of them in there that are like, oh, use this if you have boundary conditions that are in this form, this matrix will return the matrices that you would need. But I mean, if you had more special boundary conditions, you could implement them yourself as well, using all these individual parts. But so from those kind of matrices, I kind of had a question on naming conventions for them. So there's, in general, I was kind of keep them in terms of Robin, because for most of them, the Robin can support both, can support Robin, Neumann, and Dirichlet conditions, like the same implementation can support all three of them. So I just kind of leave it like that. However, I have a question of what we're naming them after. So when we do, let's say when we do a weak form of a gradient operator with scalar quantity defined in cell centers, well, we get the weak form to do the phase divergence, because that's what we have defined on that mesh. So if we're applying boundary conditions to that, should it be named after the phase divergence, or should it be named after the cell gradient, which we're approximating? And the same kind of thing applies for, okay, when we do the nodal gradient, well, we're actually doing a weak form of a edge divergence, right, quote unquote, even though that's not really defined. So should it be named after a edge divergence, even though that's not an operator we have, or should it be named after the nodal gradient? So does my question make sense?
Yeah, it's a subtle point. But isn't it like there's no gradient in that weak form? Like if the cell center is defined, like there's no gradient. Like you're approximating with the versus transpose.
Right, we're approximating the gradient with the phase divergence transpose times the volume. Like it's the weak form of the cell gradient operator.
That's true.
Right.
Yeah.
Does it work if instead of adding weak form there, if we just say like phase divergence Robin? Because I think, well, at least for me, I think having the first name match the operator is gonna simplify life, even if it's not necessarily like a true but it is like what we're applying the boundary conditions to. So like if we called it something like phase divergence boundary condition Robin, or maybe not saying the boundary condition, I don't know, does something like that kind of, please?
I don't know. I would be tempted to go gradient because literally like a face divergence, you don't need any boundary condition. Like
That's fair.
it's well defined.
Mhm.
So the problem is the transpose. And so I think I don't know, like here, focusing on the physical, what we're actually physically doing seems a bit better because gradient is like not well defined. So you need some known parameters to set that up. So, and that's basically what we're doing. So I guess I would tempt it to like use some sort of grad there rather
That's
than,
fair.
I don't know, like it's a good question. I don't know, Joe, what's the good answer?
Because if we kept the convention of naming after what it physically represents, quote unquote, it'd be okay. There'd be a cell gradient one, like a cell gradient weak form, Robin, whatever. There'd be a edge divergence weak form, and there'd be a face curl weak form. So these are like that would be the convention for that way.
Right. I would kind of tempt to do that. Because I think in the code, we actually generate the gradient, although that's actually div transpose. So yeah, I think in a weak form sense, that's probably better.
That makes sense. I'll reverse my first statement and instinct on that because I like that basically if you were writing that down, like if you're actually starting from the derivation, which is where if you are interacting with this hunk of code, you're probably starting from the derivation, then that actually seemed quite appropriate.
Okay, that's what I was leaning to as well. I just wanted to bring it up because it was an odd thing that I was like, oh, well, what I just wanted to, be consistent, want to have a consistent thing there. So
Cool.
yeah.
Oh, and Joe, another thing in flow problem is it's like because there are a lot of unused cells, and then you can actually define the boundary condition inside of the cell. Suppose you got a river, and then the head is fixed. So people use like either Neumann condition or Dirichlet condition in that domain. So this is something like if you're thinking about kind of generalizing discretize for general use, we do need like kind of that types of stuff. And I think it's not very hard. I kind of did it at some point, but I wasn't sure how to really generalize in a way that we can basically use the same operator that we have now.
Yeah, I'm kind of at this point I'm thinking of just generalizing it to the meshes themselves and assuming that the mesh is defined along the boundary. What I'm imagining for that kind of problem is that you would design a mesh, like you maybe design an unstructured mesh that would follow that, or design a curvilinear mesh that would, where the boundaries of the mesh align with the boundaries of your domain.
Or you could just discretize a tree mesh that has a river in it, and then as long as you can define your boundaries as the outer active cells, right? Can we do that? Can I take a tree mesh, chop it in half, and say my domain is like, the left half? Can I define it based on active cells?
It takes a little bit of thought. Like you kind of have to slice. You end up having to like slice things out of the gradient matrix, and, like slice rows or slice columns out of the face divergence and things like that to get rid of those cells that you're not using. It kind of, that's kind of what we're artificially doing when we're imposing the boundary condition on surfaces in, like in DC when we set frequency domain or EM when we're setting the connectivity hot or really low up there. We're creating like an artificial boundary condition there. It does the similar thing to what they are. Because if you had like an infinite resistivity in the air layer, that would force a Neumann boundary condition or a zero Neumann boundary condition at the surface. But then you could do that, and then you'd have to remove those faces from the operator. It does take a little bit of thought there. And before we go, I'd like to give a chance for Mike to show off some of his results that he posted there.
I mean, yeah, nothing too exciting to say about them, but we have some initial results there and kind of just getting them into pair view and putting some fault traces on them and gonna try to get some geology in there too, so that we can see if there's any interesting correlations to
screen.
be made.
Show it, because otherwise people on the recorder are not going to see it.
So here's just kind of our model. These are, I guess the black lines are just fault traces. And then right now, these kind of isosurfaces that we're seeing are some of the positive density anomalies that are there. So it's kind of interesting that some of them are kind of following the edges of these faults quite nicely. And then if we look at kind of the main negative anomaly is kind of this one here that's centered about kind of the main gravity low just south of the lake. And that's kind of one of the areas here that has kind of the highest heat flow. So kind of our big question will be whether we can describe all of that with like a shallow basin of sediments, or if there's possibly kind of a deeper kind of gravity low source that's there that could be related to melt of some sort. That's kind of the heat source for all that hydrothermal activity. So just kind of, that'll be some of the next steps, is trying to get some good geological constraints on the size and the depth of that basin right there, and trying to see just from modeling if that can explain most of the low that we're seeing in the data. So just kind of playing around with some of that stuff, kind of fun.
Looks like you're getting some nice dips in there, eh? We should re-implement the directional derivatives to reinforce it.
I did do some of the filtering. I used that the geoscience analyst thing that you've been working on, Dom, and I did look at some just kind of filtered maps of the data.
No, I mean in your model, things are dipping already north. They seem to be dipping northeast, right?
It could be, yeah.
Yeah. So we should try to do the gradients on the in the inversion just to reinforce those dips.
That could be interesting, yeah. Yeah.
For sure.
Yeah, it'd be fun to talk with you about that more.
So these are inversion results?
It's an area called Clear Lake, which is just kind of like 2.5 hours north of the San Francisco area, kind of at the top end of the Napa Valley. And so kind of this area, like right in here, if you guys, I don't know if you can see the cursor, but it's just south of Clear Lake itself. And it's an area called the Geysers, which is kind of one of the largest geothermal fields in the, well, I don't know if it's the country or in the world, but they have a series of like 13 or 14 big geothermal power plants there that have been active for 20, 30 years, at least. Maybe a little longer than that. I think it was probably more like the 80s that some of those started coming online.
I'm assuming are they just, so they're not like, they're just taking advantage of like the naturally occurring geothermal waters there to produce power?
Yeah, I mean, I think a lot of the field is actually steam instead of just hot water, but they have heat flow values of, I think 400 degrees centigrade if you get down like a kilometer or so. So they have some very hot steam. So I guess our big research question is if there's just kind of like an intrusion that's in there that has kind of mostly solidified and is just still giving off all this heat, or if there's actually kind of liquid, like some partial melt down there. Because that has a big impact on, I guess, the longevity of the resource and the hazards that could be associated with it.
And Mike, what are the other data that you have?
So we have some airborne magnetic data, and I guess the big data sets that we're going to be collecting once we can get back out to the field is going to be MT. So we're going to be trying to collect a lot of MT, like a fairly dense MT grid that covers this area.
I look forward to seeing that in the future.
Yeah. Yeah, no, it's a cool project. And I guess lots of people have done, there've been lots of different seismic studies that have been done, but most of those are fairly, well, they're just like maybe big earthquake tomography, like teleseismic type studies. So they're not super high resolution for just kind of looking at a smaller area like this. They're more for like large scale crustal structure in this area. So
Do you think MT would give like enough resolution to answer that question, like whether that's partial melt or intrusion?
That's a good question. I mean, if it's solidified, I don't think we're going to see a big contrast in resistivity. So I think we'll have a decent chance of being able to make some good interpretation from that. But I guess if nothing else, it'll definitely help us if we can combine that with our gravity. It'll give us a better idea of, is our low density stuff all at the surface, or is there maybe something more at depth too? Because if I guess we see a gravity, if we need some low density stuff at depth, and it's a little more conductive, then I think the combination of those two would probably point to some partial melt.
Yeah, and get your
That'd be
edges,
really cool if
get
you
your
could
edges from the
tell.
mag, right?
Yeah. So it's kind of fun. Something's coming along at least.
Well, is there anything else before we call it a week?
Quick update on my end was I worked on that airborne project and it is finished. Data will be open soon, so in a week. And they actually asked like, do you want to actually save the code and want to upload to their open data portal? So I asked like I'm kind of interested, and then we can have a small document that can point to. So yeah, I was hoping to kind of have 1D code sort of ready and then point like that 1D code and a bit of documentation to their open data portal. So that could be an interesting sort of place that we can kind of advertise SimPEG. So yeah, anyway, that's just an update. And anyone interested in that data now, you can use it. So
Well, thank you all again.
Oh, I was just going to ask a quick question. Sagi, on that note, do you have an example that when the data come out, we could include in the SimPEG documentation? It would be really nice to have, to have pointers back and forth and sort of.
Yeah, so one thing that I was hoping to be connected with one of the waterboard person, so who's working on that part, having a small, like an app that they can use and then show kind of what SimPEG could do in the groundwater problem in California. That's one. And the other thing, I was curious about the license of the data, because I think I'm not sure who can actually use that data, because it's pretty complicated format and sometimes it's not even CSV. So I was hoping if you can even like some small portion of that data into simple format like a CSV, and then hold in our Google Cloud, or so we can easily like download, or even we can just use their data portal, download, and post in our page. I wasn't exactly sure that's possible. So I was going to ask them if that's possible. Yeah, I'm happy to do that. That would be great.
That'd be super cool.
Exciting. Well, if there's no other discussion, say goodbye to everyone, and I'll stop the recording.
See you, everyone.
Thanks,
Bye.
everyone.